All right, so far we've talked about ionization energy, we've talked about atomic radius, and the third one that follows the exact same patterns as ionization energy and atomic radius is what's called electronegativity. Okay, so the electronegativity of an element is the ability of an atom within a bond to attract electrons to itself. So think about like in the carbon-fluorine bond. One of those atoms is able to attract here's the bond right here. One of those atoms is able to attract those electrons with more traction than the other one is. Okay, that's what electronegativity is which of these two can attract the electrons in the bond with more strength, with more attractive power than the other one can. Okay, now one of the things you'll find is that when you talk about electronegativity, thinking about the periodic table, that very last column over here, which we call the noble gases, those we do not include with electronegativity because, again, it has to be within a bond and they typically do not form bonds. So electronegativity is really, we talk about it here in the S subshell and the P subshell, except for the noble gases. And very similar to ionization energy, very similar to atomic radius, as you go across the periodic table, you should be able to tell me now what happens with ionization energy and what happens with atomic radius. As you go from left to right, the first ionization energy increases and the atomic radius decreases. Atoms get smaller because the valence electrons occupy the same valence shell, but you're increasing the attractive force to the nucleus because there's more protons, so the attraction gets greater. Same thing happens with electronegativity. As you go from left to right, notice excluding the noble gases, electronegativity increases, same thing as you go left to right. It increases as you go across the periodic table, and why is that? Because, again, the number of protons increase, but the valence electrons occupy that same valence shell. So in the carbon-fluorine bond here, which of those two is going to attract the electrons more to itself is the one with the greater electronegativity. Since fluorine is farther to the right on the periodic table than carbon is, fluorine has a greater electronegativity, and therefore the electrons in that bond will be more attracted to the fluorine than they will be to the carbon. Okay, as you go down the periodic table, the same thing happens. The ionization energy decreases, the atomic radius increases, and the electronegativity, just like ionization energy, also decreases. Why is that? Because there's more electron shells. The distance between the valence shell and the nucleus is greater. That decreases the attractive force. So the bond between like fluorine and bromine is farther down than fluorine on the periodic table. That means bromine has a lower electronegativity. And again, just like the carbon example, those electrons are going to be more attracted to fluorine than they are to carbon or to bromine. Okay, so one of the things you'll find is, again, taking out the noble gases, that fluorine is up here in this top right-hand corner. Therefore, fluorine is the most electronegative element on the periodic table. It attracts electrons to itself more than any other element does. Okay, and down here in the bottom left-hand corner, those elements, francium, cesium, somewhere around there, those have very, very low electronegativities. Okay, they do not attract electrons to themselves very well. Okay, so the pattern for ionization energy, atomic radius, and electronegativity, they're all the same. Okay, explain that to me in here. Okay, tell me what is that pattern, and then more importantly, why? Okay, and then as you go down the periodic table, going from top to bottom, here's left to right, top to bottom, again, the same pattern. Ionization energy does what? Radius does what? Electronegativity does what as you go down the periodic table? And then again, explain your reasoning. Up here, you better talk about valence electrons occupying the same shell, yet more protons. And down here, you better talk about more electron shells, more distance between the nucleus and those valence electrons. Okay, Now again, kind of what I showed you before, based on these patterns, the non-metal elements in the top right, so basically fluorine, oxygen, chlorine, those elements around there, have the highest electronegativities, and therefore anytime they form a bond, they attract those electrons with a very, very strong attraction, much more than other ones do. Okay? Now again, why is this important? Because later on we're going to talk about polar versus non-polar bonds, and electronegativity is absolutely a huge, huge part of whether a bond and whether a molecule is polar or not. Okay, one more quick thing here and then we'll be done for today. This is stuff you probably already know. There's periods on the periodic table. You don't need me to read all of this. There's groups. So the periods go 1, 2, 3, 4, 5, 6, 7. The groups go down, down, down like that. There are names for groups. There's the alkali metals, the alkaline earth metals, the transition metals. You should be familiar with those names. Okay, many of the elements in these groups do tend to gain or lose the same number of electrons, or they tend to have what's called the same oxidation number. I think we talked about that in Unit 0. Okay, on the AP exam, a lot of times they do ask questions about this. This will be on your test over Unit 1 about the most common ion of an element. Anytime they talk about the most common ion, you can't think of it as a nitrogen atom. If they say the most common ion of nitrogen, you look at the periodic table and you go, well, what's the most common ion of nitrogen? You find nitrogen, and remember that ions, again, here's a periodic table, goes +1, +2, +3 over boron, and then -1 over fluorine, -2 over oxygen, and -3 over, that's a 3, over nitrogen. So when they say the most common ion of nitrogen, you can't think of it as N, you have to think of it as N3-. Okay, so the most common ion of an element is the number of electrons that must be gained or lost in order for the element to be isoelectronic with one of the noble gases, to have the same number of electrons as its nearest noble gas. So again, we've got +1, +2, +3, like I already said. These are all +1, these are +2, these are +3. And then the fluorine group, the halogens we call them, are -1. The oxygen group is -2, and the nitrogen group is -3. Okay, and we will talk about that. We will continue to talk about that, but that is anytime they say most common ion, you have to think of the ion, you have to think of the charge. If they say the most common ion of magnesium, you think Mg2+, not Mg. If they say the most common ion of chlorine, you think Cl-, not Cl. They're not going to say Cl-, they're going to say the most common ion of Cl. And you have to know what that is. All right, so this next part is going to talk about some chemical reactions, so let's go ahead and wait on that until our next video.